Hello, my name is Lukas Graf. I'm a PhD student at Augsburg University. My talk will be about the price of anarchy for instantaneous dynamic equilibria, which is based on joint work with Tobias Harks, my PhD supervisor. To get us started, I want to give you a quick motivating example. So we have a road network here with cars in it, and the cars have different starting positions and one common goal, which is the node T here in the bottom right. And these cars all want to get to T as fast as possible, so they calculate the shortest path and start driving on it. Now, while they are driving, they get constant updates about the current traffic situations. So in this case, for example, the blue car now gets the information that there is a traffic jam on this right edge here. And so now it can make a choice. It can choose between two different paths, and to do that, it takes into account the current traffic situation here, which makes this path longer than this path, and so it takes the detour down to y here, like this. And now the situation where all the cars exhibit this behavior, all get updates about the current traffic situations and make their decisions based on this. This is what we call an instantaneous dynamic equilibrium. And as you can already see in this example, these decisions might not always be optimal. Here, for example, the blue car, if it had continued on its journey to the right here, by the time it would have arrived at X, the traffic jam already dissolved. So taking this detour was actually unnecessary, but by the time it had to make this decision, this wasn't obvious. It only knows the current traffic situation, it doesn't know how it will evolve in the future. And so we can't expect optimal arrival times in this equilibrium, which is why we look at the price of anarchy to measure how far away from the optimal arrival time we are. Now this example is actually an example for the discrete version of this model, so where we have unsplittable particles of a fixed size, the cars here, and the time moves in discrete time steps. For the rest of the talk, I will actually switch to the continuous model, where we have infinitesimal small flow particles and the time moves continuously. Right? But the idea is exactly the same, which you will now see when I define the model formally. And so this definition is split into two parts, the physical model and the behavioral model. The physical model consists of the directed graph, basic road network. Then all the edges have a travel time, tau e, which is just the time it takes to traverse the edge without any congestion, and a capacity nu e. And just to make the pictures in this talk simple, for all the pictures, I will always have the travel times to be 1, and the capacities are either 1 on these thin edges or basically infinity on these thick edges. And we also need an additional definition. We define tau to just be the sum of all the travel times in the network. Then we have our common sink, where all the flow particles want to travel to. And the flow particles enter the network as indicated by these network inflow rates at the nodes. So for example, at this node, a flow enters at a rate of 3 over this time interval. And all these inflow rates are finitely lasting, and we will assume here that the time the last particle enters the network is at time 0. After that, no new particles enter the network. And again, we need a additional one, which is big U is just the total flow that will ever be in the network, right? The integral of all the inflow rates summed over all the nodes. And now we can observe the same behavior as before, right? The flow enters the network, tries traveling to the sink T, and when the flow enters the network at a higher rate than the capacity allows for example here, then we have a congestion, which we will now model by such a Q at the beginning of the edge. Right? So if the inflow rate is greater than the capacity, a Q forms at the beginning. And this Q will now influence how the other particles behave in the network. Right? And as before, we have a congestion on the right, so these flow particles arriving at W will now take the detour down to Y, like this. To formalize this behavior, we need our behavioral model. And first we define a current travel time, which is just for any edge E and time theta, the current travel time is the physical travel time over this edge plus the current waiting time on this edge. Right? The length of the Q divided by the capacity. And with this, we can now define what an instantaneous dynamic equilibrium actually is. We will call this IDE for short. And a flow is such an IDE if whenever particles enter an edge, this edge lies on a currently shortest path. And by currently shortest, I mean shortest with respect to these current travel times. Like this. And so if we look at our example again, we now have this queue here, but this queue will now deplete. And we have a queue starting to increase here. So from now on, actually, this path will be longer again, because we have an increasing queue here, a decreasing queue here, and now these particles will go to X again in an IDE, like this, right? Because this path here to the right is now currently shorter. So this is what an IDE is. And now we want to measure its quality. So we define the price of Anarchy. Well, first we have to define what we actually want to optimize, and this is the arrival time of the last particle, which we call the termination time of the flow. So the termination time of the flow is the first time after zero, so after the last particle entered the network, where there is no particle in the network left. Right? So the total flow volume in the network is zero. The first time this happens, this is the termination time of the flow, and we want to optimize that. And now we can define the price of Anarchy, which will be parameterized by our two parameters u, the total flow volume, and tau, the sum of all edge travel times. And then the price of Anarchy is, well, the termination time of an IDE flow divided by the termination flow time of the optimal flow. And we build this supremum over all networks with these two parameters, so over all networks with total flow volume u and sum of edge travel times tau, and all the IDE flows in this network. And so this gives us an upper bound in how bad IDEs can be compared to the optimal flow. And now we can turn to our main question for this talk, namely, what is the termination time or the price of Anarchy for IDEs in single sync network? And I want to answer this question in two parts. First, I want to give you an upper bound on the price of Anarchy, and then I will give you a lower bound on the price of Anarchy. So let's start with the upper bound. And we first want to look at a simple case, namely at acyclic networks. Right? So in this case, well, we don't have cycles, so the particles basically always travel forwards, right? They always travel in the direction of the sink. So it should be pretty obvious that there is a termination time, there is some point in time where the flow terminates, but the question is, when is this? Right? So let us think about what's the worst thing that can happen to our flow. Right? So we are one particle, and we think we are maybe as far away from t as possible, like here. What's the worst thing that can happen? Well, maybe we take the longest path, right, which is this zigzag path in this case, like this. This is bad. And what other bad thing can happen? Well, maybe we have to wait in a queue, in a very long queue. So let's say the longest possible queue, right? A queue of length u. So every other particle is before us. So this should be the worst thing that can happen, right? We have to wait in this queue here, behind every other particle, and then we take the longest path. This is the worst thing, so there should be an upper bound, which is what this lemma says. Now, to actually prove that, it's a bit more complicated, because we are kind of assuming here that we can't be blocked by the same particle twice. Right? We wait behind every other particle, and then we don't have to wait ever again. This is what I say in this picture. But this is actually not true. The same particle might block us twice. Right? And this is why this simple intuitive idea is not a proof for this bound, but we can actually prove it. It's still true, this bound. And this proof goes basically like this. So you take all the nodes, you give them labels based on what I call the pessimistic distance to the sink, so just the longest path from this node to the sink. For example, for this node, well, we can reach the sink via an edge of length 1, but we also can reach it via a path of length 2, like this. So it has a pessimistic distance of 2. And then for every such level, right, of distance, we define the flow that is closer, the flow volume that is closer to the sink at every time. So for example, if you take k equals 4, then f smaller or equal to 4 at time theta is just the total flow volume closer to the sink than this dotted line here. Right? And so basically we want to prove that at some time all the flow is closer to the sink than 0. So it is at the sink, and then the flow terminates. Right? And we show this by giving such a lower bound on this flow volume closer to the sink. which you can show just by induction, that this always holds this bound. And then with this claim, we can just plug in here again k to 0. So we have just the flow that is at the sink. And for theta, we take our bound. And then if you plug that in, you get that at this time, at least u flow volume is at the sink. And so all the flow is at the sink. And so our flow terminates, which gives us this upper bound for acyclic networks. Okay, so we have an upper bound on the termination time for acyclic networks. Now we want to get to general networks. So we still have this lemma. And if you think about this for a moment, we don't actually need acyclic networks for this bound. The only thing we actually need is that our flow only uses an acyclic subpart of the network. And well, if there are no queues in our network, then this is true, because all the shortest paths are an acyclic subgraph, and in an IDE we always use shortest path. And if there are no queues, this is a static acyclic subgraph, so the lemma still holds. And even more is true if we only have very small queues. Let's say the sum of all the queue length is at most a half. Then these queues can't divert us away from an actual shortest path, or a physical shortest path, because the queues are just too short to do that. Any longer path will be at least one longer, but the queue only can make a path a half longer, because we don't have that many queues. So with only small queues, IDEs still only use a static acyclic subgraph, and so the lemma still applies. Right. Turning this around, this means we only have a problem if we have large queues. So let's look at our example from the start again, where we had large queues, right, like here. And let's also make this graph have a cycle. We add this edge here. What happens now? Well, this flow here arrives at the bottom and sees a large queue here, a small queue here. So what will it do? Well, it will go up here, like this. And then it will arrive here. And if you remember, this is the place where this flow actually started. This flow has now completed a whole cycle, right? It traveled in this cycle. And thus, it's not even clear in general network whether IDE flows even terminate, right? Because we can have such a flow traveling in cycles. And maybe this continues, right? Our flow goes back to the right. And by the time it arrives on the right here, we again have a big queue here, small queue here, no queue actually. And so we go back down again. So now the situation has changed again. Well, now the shortest path is going back up. Can this continue forever, right? Then we don't have a termination time. Well, to see that, why is our flow trapped in a cycle here? It is trapped because there are other flow particles which are blocking it, here and here. Can this keep going forever? Well, no, because these flow particles are actually closer to the sink, and in this example, all the flow particles from this queue, once they leave it, they immediately vanish into the sink. So whenever we are blocking our cycling flow here, by flow particles here, we lose some flow. The blocking flow then vanishes into the sink, right? And since we only have a finite amount of total flow in this network, this can't happen forever. At some point, all the flow that is closer to the sink and therefore can block us has vanished to the sink. And so we achieve some time where all the queues on edges closer to the sink are actually small. Now we are in the case of the observation, and therefore we terminate. So we know IDE flows still terminate. But okay, we want to get an actual bound on this termination time, so a bit more careful analysis is required. But we want to use the same idea here. So basically, we want to look at this subgraph, right, which was the graph that was always blocking us. But now it isn't anymore because there are only small queues. And the effect of that is that this subgraph actually acts like a sink, right? There are only small queues here. We can't be diverted away in the subgraph, so it kind of attracts all the flow. And all the flow that arrives here in the subgraph, this will vanish into the sink because there are, again, no queues in the subgraph. And this leads to the following definition of a sink-like subgraph. So some subgraph of a network is called a sink-like subgraph for some time interval if, well, I want to say the flow volume in it over this time interval is small, and we will define this by saying the current flow volume at the start of this interval is small, and the total inflow into our graph over this time interval is also small, right? So this means that there is not much flow in the network for the whole, in the subgraph for the whole time interval. Now, why is it interesting? Well, now this is basically our new sink. And now we can again look at the node that is closest to this new sink, like this. And we can think about whether we can maybe add this node to this sink-like subgraph and make it bigger. And this is basically what the following lemma says. If you have a sink-like subgraph and you take the closest node to this sink-like subgraph, then you can add it, and this new graph is still sink-like for a slightly smaller time interval, right? It's slightly smaller. And to prove that, well, we look at the situation. We want to add this node v, which is the closest to our subgraph. Now, because it's the closest, we immediately have that all the shortest paths are still part of this new subgraph, which is one of the conditions here. And now we have to make sure that the total flow volume in the subgraph is still small, right? And this is not clear because we are adding some edges, right? These edges are now newly part of the subgraph, so they bring some flow volume with them at the start of the interval. And we also have new edges which bring inflow into this new subgraph, right? And we have to show that adding this still keeps us below 1/2. And this is true because all this flow on these orange edges, because H is a sink-like subgraph, all this flow will actually travel directly to H. It will arrive at V and then go directly over this red edge here into H. And thus, it's already accounted for by this cumulative inflow into H over the longer time interval. Right? So all the flow on this edge at the start and coming over these edges during the time interval, during the shorter time interval, will actually arrive in H during the longer time interval. So it's already accounted for, and so we still have this upper bound of 1/2 for the total flow volume. Yeah, this shows the lemma. And now we can use this to actually get an upper bound on this termination time here. And the termination time is 4 times u times tau. And to show this, let's look at the sink, the actual sink node. Well, if the sink node is sink-like for a long time interval, like this, so there's basically almost no inflow into the sink, then we can extend it by adding the closest node, the next closest, and so on. And finally, we will have that the whole graph is sink-like at the start of this interval. But if the whole graph is sink-like, the total flow volume in the whole graph is small. Therefore, we have small queues. Therefore, we terminate. In other words, if we don't want to terminate, right, well, we have to have some inflow into the sink in every interval of this length. Right? It has to be at least 1/2 inflow. And how long can we have that? Well, we only have u total flow volume, so we can have this 2 times u times for every interval of this length, which gives us exactly this bound. And with this, we can now bound the price of Anarchy, because in an optimal flow, we still need at least some constant time for termination, and so the price of Anarchy, right, the quotient of this termination time by the optimal one, is in O of u times tau. So this gives us our desired upper bound. Like this. And now, for the second part of the talk, we can turn to the lower bound. Right? Now we want to show how good is this actually, this upper bound. And the idea here is to again look at the example from the beginning, where if you remembered, we had 2 parts. Right? We have this flow cycling here, and this part. And it is cycling because there are queues blocking us in this part of the graph, right? So basically the graph is divided into 2 parts. A cycling path, where our main flow travels around in cycles, and a blocking part, where this flow blocks us. And so to construct our instance for the lower bound, we want to use this idea. So we want to construct a graph, a network, which consists of a cycle and a blocking part. So, okay, cycle, that's easy. We just have a large cycle. And now, from now on, there are edges which have a longer travel time than 1. For example, these long edges actually have a longer travel time. And now we also have a blocking part like this. And as you can see, this is our connection to the sink. And it starts with an edge of a very low capacity. So when our flow enters the network at this node S, it will first start traveling down here. But it will immediately create a queue because the capacity is small here. And so at some point, we are diverted to the right because there's a large queue here, like this. And now by the time we arrive to the right, well, the same thing happens again. We have a queue, an edge with low capacity, so a queue builds up here. And at some point, we have a large queue on the right, we have no queue on the left, so the flow goes back to the left. Right? So this is exactly our cyclic behavior we want to have. Now the only problem left is that for doing so, we need a lot of blocking flow. As you can see here, the flow basically arrives at a constant rate of 1 at the sink. So we are losing flow at a rate of 1. And this means this can continue only for time u, because u is our total flow volume. And so we only get a lower bound of u. That's not good enough. So what we have to achieve is that the same flow particles block us more than once. And to do that, right, to use them more efficiently, we basically take the blocking gadget, copy it 3 times, and set it together like this. And what happens now is, basically first the same thing as before. A queue forms here, flow is diverted to the right, queue forms here, flow is diverted to the right, queue forms here, queue forms here, and now flow goes to the left. So we have the same behavior as before, just a bit more queues, but they are all smaller. So we still use the same amount of flow. And now by the time the flow gets back here, well, now the flow from these 2 queues meets again at this node and forms a larger queue here. So by the time this amount of flow arrives here, there's already a queue waiting here, so we are directly diverted to the right. And as you can imagine, by the time the flow arrives at this node, this flow here has built up a queue here. And so we are diverted back again to the start. So we have been blocked twice by the same particles. And now we can continue this construction, right? We can again take our current blocking gadget, copy it 3 times. Now we have an instance where we are blocked 4 times by the same particles. And in this way, we can actually be blocked quite a few times by the same particles and get a better lower bound. So now I can show you the actual instance that gives us the lower bound. It looks a bit more complicated, but has the same ideas. So we have a cycling part, right, this big cycle here, a blocking part. Now we pair up always 3 of these downward edges, because this is what we actually need for the flow to behave as I just showed you. But then all the stuff happens right the way we had it in our idea. Right? And now we can calculate the termination time in this new network. And this network is parameterized by 2 parameters, k and l. And the termination time is then L times K times 3 to the power of K, basically. And if you now compare this to our tau and U in this network, you can see that this termination time is actually not linear anymore in these 2 parameters, U and tau. So this gives us an actually interesting lower bound on termination time. And so we can also use this to get a lower bound on the price of anarchy. To do that, we have to understand the optimal flow. To make that easier and the optimal flow better, we add something to the right here, like this. And now there are actually 3 basic paths to the sink. This one with length 3, this one with length 2, and the one through the gadget, which we already know what happens there, right? Now our IDE flow, it starts here. It sees the shortest path, so it goes immediately to the left. But when it arrives here, well, a queue forms on this edge of low capacity, and then the main amount of flow is diverted into our gadget, and then everything happens as before. So we have basically the same termination time. On the other hand, our optimal flow, well, it sees that actually this path is probably the best one, because we have travel time of 3, and so it will send almost all the flow this way. We have capacity infinity, so no queues there, and some of the flow here, this route, but at the end we have a termination time which is basically 3, a bit less than 3, right? So in this way we get an optimal flow which has constant termination time, and an IDE flow which still has this termination time. And so the price of anarchy is basically just this value, and if you now express this value in terms of U and tau, we get that the price of anarchy is lower bound by U times the logarithm of tau. And this gives us our desired lower bound, which we can fill in here. And now, as you see, there's still a bit of a difference between upper bound and lower bound, so there's still work to do. They are not tight yet, but we have some idea now in between which bounds IDE flows always lie, right? How bad can they become? Well, somewhere in between these two bounds. And this concludes my talk. Thanks for your attention, and I'm looking forward to your questions.